Hello, everybody. My name is Piotr Luszczyk. I'm from the University of Tennessee, and I'll be talking to you about today about the use of OpenMP in Exascale numerical libraries. My co-authors are Hartwig Ans from Karlsruhe Institute of Technology, and my colleagues from the University of Tennessee, Mark Gates and Stanimir Tomov. Let me start with talking about the scope of the libraries and the platforms that they target. So on the left is a lot of detail about these libraries. We have 4 of them: Ginkgo, MAGMA, Plasma, and Slate. And they roughly correspond to sparse methods and iterative methods for Ginkgo. MAGMA is mostly dense linear algebra and eigenvalue in SVDs, and includes also some iterative methods with preconditioners and sparse storage. Plasma is mostly a dense linear algebra, singular values and eigenvalues, and it targets OpenMP for tasking. And finally, Slate is a distributed version of the libraries that I mentioned. It mostly covers dense linear algebra and targets GPUs, as well as some sort of an interconnect that it accesses through MPI. These are exascale libraries because we target, optimize, and develop on daily basis for large installations at DOE and other facilities. So on the right, there are some examples of those: NVIDIA with CUDA 10 and 11, AMD with HIP and ROCm platforms, and finally Intel and DPC++ development platform. But the overarching goal is to show how these are just lower level bits, and on top of it is OpenMP. And the testing is performed with the continuous integration and continuous development that we have set up on x86 power and ARM processors. So what is our general portability approach to make these libraries portable and at the same time perform very well on multiple targets? So we try to stick to common interfaces that have been established over the decades, and they were developed in some of our groups. And these are mostly BLAS and LAPACK libraries that now have been implemented and ported and optimized on multiple platforms and accelerators by vendors. So this is an example of a call to matrix multiply, and it's different naming depending on which library you use, either HIP, CUDA, or perhaps MKL. We use a lot of abstractions, programming abstractions that take user data and provide very practical object structure that maps this data to a lower level hardware constructs. And we focus very heavily on the user experience. So when they encounter these libraries, they have a very easy time to express their algorithms that mostly pertain to matrices, vectors, and things such as execution policy. So the user can specify whether they want to run it on the host, on the device. And a lot of our algorithms are very generic in the sense that we program against generic data types, and they get specified down at the lower levels. And the testing is mostly done on concrete types to test whether the libraries work across the important matrices and vectors and their elements. So in Ginkgo, we have an OpenMP backend that basically makes the functionality of the entire library available on any hardware that supports OpenMP, and that would include pretty much any modern CPU processor. Because the sparse calculations are loop heavy, we have very ubiquitous use of parallel 4 throughout the entire code base of this particular backend. But because we want, for sparse operations, we want memory utilization to be very, very high, there's very advanced use atomics. And there's also not just simple atomic statement, but a lot of code specifies whether the atomics are read, write, or perhaps update. And that allows the OpenMP to optimize very well and use the memory of the target very well. And there are also very clever reductions that are necessary for the sparse operations that go either across rows or columns, depending on the sparse storage format. And Some of the reductions are very standard that you would use in most textbooks, such as arithmetic reductions and logical operators. The first ones are mostly for arithmetic. The others are for the matrix structure, but there are also declared reductions that are very specific to sparse operations on sparse matrices. And if you compare that approach to the approach taken in Ginkgo to maintain its CUDA or HIP backends, you can see that the image gets immediately much more complicated. So porting the CUDA backend, there was an initial backend in the Ginkgo library to HIP required a lot of redesign and a lot of code motion that is exemplified right here with this this flow diagram that kind of tells you how much code lines were moved from between CUDA and HIP and to the common components. So that required redesign. However, the moving from one target, OpenMP target, to another does not require this kind of code reshuffling. It just comes out of the box. Again, this is to stress the situation of OpenMP, that it remains the portable and efficient target for most of the places that support OpenMP. And we know from the users that this is the reference implementation that most of the others are compared against, especially for the correctness. CUDA and HIP are relevant alternatives for Ginkgo, and they would give you a good performance on their relevant hardware targets. But of course, as I mentioned, they required porting. And so the saving grace for the porting from CUDA to HIP was that there's a lot of similarity in syntax. There are already a lot of tools available for making this porting exercise. And also as part of the porting exercise, which partially made it hard, is that the performance had to be roughly comparable between the CUDA and HIP backends. And it wasn't just a matter of functionality, but also performance, because that's what our users expect. So moving on to another library that was also developed primarily for GPUs is MAGMA library. So MAGMA library is actually not just a GPU library. It has a lot of hybrid algorithms. And what it means for the MAGMA library is that both the host processor and the accelerator, they are engaged throughout the algorithm and have to remain efficient. So that means that MAGMA has to maintain a very efficient implementation of the host processor code to keep up with sometimes very heavy accelerator heavy nodes of these modern exascale platforms. So we use OpenMP to maintain this this very high parallelism whenever we cannot access BLAS or LAPACK libraries. So OpenMP reduces our development effort on the part of the CPU part of the algorithm, and some portions might be very actually numerically sensitive, and for those we use more advanced features in OpenMP. And if you look at the functionality that is developed in MAGMA, but is relevant on the accelerator side of the hardware stack, there's a lot of scope and a lot of algorithms that actually expose over time some problems in the vendor stacks. So these have to be fixed, and they were part of kind of the development effort that had to be undertaken, just like I talked about it during the port of Ginkgo from CUDA to HIP. And right now, we can say that a majority of the functionality of MAGMA is available and is functional. And most of it has actually very good performance and is available for download. So just to give you a taste of the results of MAGMA on a platform that is not original CUDA platform. In this case, I'm showing from MI5 and MI50. On the left is compute-intensive code that achieves very high performance. you can see that the chart on the left shows the numbers in gigaflops, and the higher value is better. And we are comparing the HIB blast versus the blast that is available in MAGMA that we called HIB MAGMA. And so you see that the performance approaches very closely the theoretical peak for matrices of sizes from about 1,000 to 20,000. And on the right is an example of a kernel that is memory bound. And for this particular kernel, the performance is a little bit lower, but also a good performance is achieved. So so this is the portability effort in MAGMA. Now moving on to the Plasma library, let me first start with showing the software stack of the Plasma library. So you see that the on the right, heavily featured in this diagram is OpenMP. In fact, Plasma would not be able to exist in its current form without OpenMP, because Plasma is based on OpenMP tasking and data dependence clauses. So you can see that on the multi-core hardware, it uses either the task pragma, or it uses task loop pragma to create a lot of tasks for the platform, and also uses data clauses to track the dependencies between these tasks. And I will talk about how these are achieved in the next slides. And for the accelerators, with Plasma depends for OpenMP for data transfers and offloading of the kernels to the accelerator device. So let's now move to why OpenMP tasking is very important in Plasma. So this is an example of a linear algebra operation called Cholesky, and Cholesky allows us to use a factorization and later on perform the inversion of the matrix using that factorization. And at higher level, this is three independent operations. One is called DPO-TRF, the other one is DLA-UUM, and the final one is DTTR-TRI. Again, the names are very meaningful for the practitioners, but perhaps they are less meaningful to common users of OpenMP. The point is that the first step is a computationally heavy factorization, and the next two steps perform the actual inversion. And if you look at the tasks that are involved in this operation, they are represented as direct acyclic graphs that are on the right. And so data tracking in OpenMP allows us to operate on these DAGs very efficiently and do the optimization on the fly without actually coding any of this optimization inside Plasma. So let me show you exactly what I mean. On the left are the two DAGs. One is the DAG when we actually treat each operation, the factorization and inversions, as a separate operation, so the DAGs have a barrier between them. On the right is exactly the same DAG, but now it is merged into a single DAG, and the only difference is that we actually draw arrows between the tasks in those three DAGs, and we merge them together based on the data dependence. And the data dependence is tracked fully by the OpenMP runtime. And so what does it do to the performance is shown in this slide that shows the up on top, the trace when we have all these three DAGs as being independent of each other and not communicating data dependencies between one operation and the next. Down below is what happens when we in Plasma just allow the OpenMP to manage the data dependencies and the parallelism in between those DAGs. You can see that because the time passes from left to right, as is the case for most of the traces, you can see that there's a very large reduction of the time to complete the entire operation, to the extent that the last operation, the light blue colored tasks, are mostly for free, because that time is reduced due to the overlap and tracking the dependencies automatically by the OpenMP runtime. So let me just move finally to the last library in my presentation, which is Slate. And Slate, as I mentioned, combines a lot of things from the previous 3 libraries, and it targets a lot of things, a lot of hardware platforms that the other libraries target. But in addition to those, so in addition to the multi-core processors and the GPU accelerators, it also targets a distributed memory. So it has to use some sort of a library. In our case, for portability, we use MPI in a multi-threaded mode to communicate between the nodes. The algorithmic scope of Slate is very large and growing with every release. So we have all the dense algorithms that you would expect in libraries such as MAGMA or LAPACK or ScaleAPACK. We also have different matrix types and storage format to cover all the cases that a lot of applications require. And we also have a new breed of algorithms that are they are data sparse. They take advantage of low rank of the data, and they allow for much faster execution. However, in a sense, to coordinate all these pieces, so the GPU kernels and the multi-core processors and the invoking of MPI, the coordination is done by OpenMP tasks, and data dependence tracking that is done by OpenMP. It is quite similar to what happens in Plasma. Again, this is a short presentation. I don't have the time to go into the details. I encourage you to visit the webpage for more details. And finally, let me finish by encouraging you to look at other videos for the OpenMP available at the SC20 conference. Thank you very much for your attention.